All right. Let's see. I think this is the time where I'm supposed to start. I think I was supposed to start 2 minutes ago. But then, you just get a chance to get everyone into the room. That's my excuse, and I'm sticking with that. My name is Mark Seemann, and if you want to know more about me, there's information there on blog.plur.dk, so I'm not going to tire you with that. Also, on Twitter @plur. Apart from being a freelance software developer, I also give conference talks like this one. So a couple of months ago, I was in Kiev in Ukraine giving a conference talk there, and I was talking about what we can learn about dependency injection from functional programming languages like F# and Haskell. It's not the talk that I'm giving today, it was another one. And after the talk, people came to me and started talking to me, which is a perfectly normal thing. You're welcome to do that as well. And one of the common questions that I kept getting was, okay, so you showed us all those cool things in F# and in Haskell. How do you apply those things in C#? I'm sort of thinking a little bit about the answer to this problem, or to the question. And I'm basically beginning to arrive at the conclusion that it's fine that C# is getting some of the functional language features like lambda expressions and stuff like that. But trying to turn C# into a strictly statically typed functional programming language is not really going to take your code base to a place where you want to be. People weren't really happy with that answer because obviously you'd like to get an answer that you can do these things. But okay, that's the best I could come up with at that time. So I gave another talk. I actually repeated the talk in Moscow a month later on, and afterwards people came and asked me various questions, and one of the questions that kept coming up was, how do you apply all those cool techniques to C#? So you can sort of see a pattern. This is a question that I get asked over and over again. And again, I answered that, well, you can do some things, but really trying to go fully functional in C# is not going to make, you can't harvest the benefits of functional programming by doing that in C# because it's going to make your code look absolutely horrible. And people, they didn't really believe me, so I decided, okay, I will now show the world just how horrible it can be. And that's the talk today. I kid you not. That's my plan. I will show you the most horrible C# code you have seen. No, you've probably seen a horrible C# code, but I will show you horrible C# code in a completely different way of horror, if you will. In order to do that, we need to look at some example code. So I always like to use the same scenario for my examples, if I can, and that of an online restaurant reservation system. I always use this scenario if at all possible, but I keep remixing and changing the code examples. So just to make sure everyone understands what we're talking about, you want to make a restaurant reservation. You go to you find a form, you fill in the date and your details and so on. This is my real email address. All the spammers already have it, so you're welcome to use it as well. So you fill in the form, you click submit, it creates some sort of JSON document that gets posted to some sort of web server, and the thing that we have to do is we have to figure out how to implement the web server. And we're just going to look at a small snippet of the business logic there, not even the entire web server stack. And we just see what's going to happen if we try to make it fully functional and sticking in C#. Now, since we're doing a dependency injection, I think this is a good thing to see if we can turn that into a fully functional thing. We will define an interface because that's what you do when you do dependency injection. You could use an abstract base class as well, but it's not really important. So we really have a database with some reservations inside of them, but in order to comply with various enterprise things, we call it a repository, even though everyone knows it's a database. So here's our database with the reservations inside of them. And there's a couple of things we can do. We can query the database, read all the reservations that are already registered in that database for a particular date. Gives us a collection of reservations back. We can create a new row in the database. You'll notice I'm using the create, read, update, and delete terminology here. I'll just stick with those two methods though. The reservation method or the create method returns an integer. That is the ID of the row that that you just created in the database. So this violates the command query separation principle, but it's a common thing that people do. So I'm just keeping the example here realistic. Now, I want to add a third method just to make things a little bit more interesting. And the third one is doesn't really belong here, but let's add it anyway. So we want to be able to figure out whether a reservation is in the future or in the past, because it doesn't make sense to accept a reservation for a date in the past. Now, this method really belongs on a different interface, a different abstraction, but we'll just put it on this reservation repository for the sake of the example. Otherwise, it's going to get way too complicated. Okay, so if we assume that we're going to take that repository and inject into some sort of class, we can now try to make a little bit of a business decision of whether we can accept the reservation or not. So we'll have an incoming reservation, and we'll try to figure out whether we can accept it. So it will return a nullable int. And the contract here is the idea is that if we accept the reservation, we will have created a new row in the database, and that row has an ID, and that becomes the ID of the reservation, and we'll just return that. If for some reason we have to reject the reservation, we'll return null. So the first thing we could do, if we have if we injected this repository from before into the class, via the constructor, then we could access it, and we could say, is reservation in the future? That returns a bool. If that bool is false, we'll return null immediately. We know that we can't accept that. That was some sort of input validation error that failed there. Otherwise, we can move on. We can query the database. We can say, read reservations with the reservation date. That gives us a collection of reservations. We'll just do a sum over the quantities. That gives me an integer. That is the number of reserved seats for that particular date. So I'm sort of ignoring that there may be tables that are not completely filled. So you can imagine this is one of those fancy restaurants that just has one big table and everyone has to, dine communally together. It's probably in New York somewhere. Right, so we have a number. We need to figure out whether we have enough remaining capacity. So if we know the capacity of the restaurant, that's another number, we can make our business decision. We can say if we have too little remaining capacity, or if the capacity that we have is less than the number of reserved seats plus the requested quantity there, we also reject the reservation, and we do that by returning null. But otherwise, we can move on. We can set is accepted to true. We'll call the create method on the repository. That creates a row in the database. It returns an ID. We just return that ID. C# has an implicit conversion between int and a nullable of int. So this compiles, this works, and gets the job done. There's nothing wrong with this at all. So in an effort to make things more complicated than they can be, someone would then say, but how do we do this with functional programming? So let's have a look at that. Before I launch into this whole thing, I want to make a little detour, because the detour will hopefully be instructive. So here's the reservation repository interface again. I've reordered the methods a little bit. I put reservation in the future on top because this is the order that we actually end up using them. So maybe this is a little bit more intuitive, I hope. When you're interacting with the database, what you're really doing is I/O. So you might want to say, let's make it async. This is not really what I want to do for the rest of the talk, but this will be instructive, I hope. So we can see what happens if we make it async. Basically, what you need to do to make it async is that you just, instead of returning normal values, you just return tasks of those things. So task of bool, task of a reservation collection, task of int. So with modern C#, that's not really a big change, because you just take your try accept method from before and you just sprinkle async and await keywords in the right places, and then it still works. So there's a magical, language feature there. But the thing is, the TPL, the task parallel library, that technology existed before the async and await keyword were introduced into the language. So before you had async and await, you could still write this code, but it wouldn't look like this. It would look something like this. So what you would need to do is you would say, well, okay, let's call is reservations in future with the reservation. Now that's going to return a task of bool. So that's not what we want. We want a task of nullable int. So we can't really move on until that task has completed processing. So what you need to do is you need to call a method called continue with, and you can see it happens three times here. And continue with, the idea here is that you now have to supply a code block that tells your code what happens when that task has completed. So you get a task in its completed state, as input into the code block that you supply. So T1, T2, and T3 there, those are completed tasks. So what you can do is, and what I've done here is I continue with the code block in the form of a lambda expression. So T1, for example, is the completed task that, comes back when is reservation in future has evaluated. So what you can do, then you can say T1.result, that's a Boolean value, and then you can do normal if things on that one. And T2.result further on down, for example, that's a task of reservation collection. So, taking the result out of that will just give you the reservations and so forth. So this idea about having a step, a task, and then, after the task is completed, you tell the code what needs to happen next. And the way you do that is you supply a function or a piece of code that sort of handles, what happens next. So you'll notice one thing, the output of the task becomes the input to the continuation. So T1, for example, is the completed task. The result of that is a Boolean value. So the output of figuring out what the time is, or whether the reservation is the future, becomes the input to the continuation. And that's the same pattern that goes on in all three cases here. So the code becomes more complicated, but this is basically what we need to do when we want to shift into doing something in a functional style. So we will have not task of T, but something of T, and we will sort of need to do continuation parsing style in this way, where we say we'll start something, and then when that completes, we will have a continuation function that takes the result of the previous steps as input, and then continues with that. So that's sort of the intuition. So this is just why I wanted to show you this before we got started with the real functional stuff. Now, how do I do dependency injection in Haskell? Well, you don't, because Haskell is a functional language. Fine, it's functional. How do I inject dependencies? Well, you use a free monad, which allows you to build a monad from any functor. Did you just tell me to go fuck myself? I believe I did, Bob. So, apart from being funny, there's quite a bit of truth in this little comic here, because first of all, it's true that if you ask a certain category of functional programmers, they will give you that answer, and they will just expect you to understand what they say. They will expect you to understand what is a free monad, what is a functor. So on that level, that answer is usually not particularly useful. But another thing about this is that it's actually true. This is how you do dependency injection in Haskell. What's one of them? There's a couple of different alternative options there, but it's one of them. So you can absolutely use a free monad in order to model, how that works. So I'm just going to be that guy and just launch into do free monads in C#. How about that? It's not going to be fun. So I'm not expecting you to know what a free monad is. I'm not expecting you to really know what a functor is, although that's pretty easy. We'll get to that in a moment. What my agenda here is, I'm trying to show, what will happen if you try to go all the way to functional programming in a language like C#. So let's see what we can do here. So we have this repository interface there, and we want to figure out how to do this in the functional style. So if we want to turn it into a free monad, there's actually a recipe. So I'm not really going to try to explain to you what a free monad is. I'm just going to show you that there is an automatable process for translating a C# interface like this one into a free monad, and it goes in a lot of steps. So if you really want to know all the details, I have a blog post that walks you through this in very elaborate details. But basically what you need to do is you have to start trying to figure out how to turn an interface like this into a functor. So what's a functor? Well, you probably know link in C# already. You have a list of integers, and you can call select on that, and then if you say for each of the integers inside of that list of integers, I'm just going to turn that into a string. Now you have a list of strings instead of a list of int. So that ability to take a container of something and turn it into a container of some other generic type, that is basically what a functor means. It doesn't have to be much more complicated than that. And C# already has the language feature to do that, because link was built around this idea about functors and monads. So the select method is what we call the structure-preserving translation of the stuff inside of the container. So we need to figure out how to do that. This is not a functor at the moment. So the trick is to say the three methods defined by this interface, we're going to turn those into a little domain-specific language. And the vocabulary of that language will be those three methods. So it's not going to be a Turing-complete language. It's going to be a very little, limited, small domain-specific language that just consists of three instructions. So the first thing we do, what I'm going to do now is I'm going to translate, I'm going to follow my recipe for translating this into F#. And again, I'm not assuming that you can necessarily reach F#, but the syntax here, I'm just going to use some type declaration syntax. I'm actually not going to write, functions, so that's going to be okay, I hope. I'll talk you through it. Now, following the recipe, this is almost like an automatable recipe. What we do is we say we'll need to create a new type. This new type should be generic. We'll call it something a little bit different because we'll typically call it something instruction. In this case, I decided to call it reservations instructions. And this prime A, this is just the F# syntax for writing a generic type argument. So in C#, this would have been capital letter T, but here's A. Now, the next step in this recipe that you can follow, and you can probably write a program that did this for you if you wanted to, is to say, well, for each of the methods in the interface, you create a case. So what you're starting to do here is what we call a discriminated union, something that can be one of multiple mutually exclusive cases. So the first case, we just take the first method and turn that into a case, and the name of the case is just the name of the method. So we just call that case is reservation in the future. And when you're trying to turn an interface like this into a little DSL, which has to be a functor, the contents of each case will always have to be a tuple. So this is how you create tuples. I left some space there so that we can have some type annotations there. But it's just the brackets, just say here comes a tuple, and the star in the middle just means that that's the delimiter between the types in the tuple. And the recipe then says that the input value or the input type of the method that we are mapping at the moment should be the first tuple. So we'll just say that it's going to be a tuple where the first element is a reservation. And then the second element in the tuple should be a continuation function. So remember I showed you this TPL example with continue with before where, after you've completed one step, you continue with something else. So the idea here is that we have sort of abstracted away the idea of figuring out whether a reservation is in the future, and we can delegate that to some sort of interpreter of our little domain-specific language later on. And then when the interpreter is done interpreting, it'll call our continuation function with the result of what it figured out. So that means that just like in the TPL example, the output of our little operation there is reservation in the future becomes the input to the continuation function. And then the continuation function should take that as input and return a value of the generic type A. Now, if you didn't get all of this, this is perfectly okay. I'm just trying to demonstrate to you that I'm following a recipe here. You don't have to think in order to do this. You can basically just write a program that did that if you wanted to. So we'll just continue on with the next one. I'll move a little faster now. So we know that read reservations also has to be a tuple, and the second element has to be a function that returns the generic type A. So we'll take the datetime offset, which is the input to the method, and we'll make that the first element of the tuple. And then we'll say the output, the read-only collection of reservation there, we'll just turn that into reservation list, and that will be the input to the continuation function. And we'll map the create method in the same way. There's a case called the create. It takes a tuple, or the content inside of that is a tuple of reservation and a continuation function that goes from int to A. So again, if you're not entirely following this, it's okay. The real point is to show you that this is actually translatable back into C#, and I'll show you how to do this in a moment. But you're not going to like the result. So let's remove the interface there and see what we have so far. Now, in F#, this is called a discriminated union. So the idea of a discriminated union is it's a type that statically is known to have, in this case, three mutually exclusive subcases or subtypes, if you will. So you can think of it a little bit like an object hierarchy, but the difference is that it's not extensible. It is very deliberately not extensible. So we know that there's only going to be those three cases. And not only do we know that, the compiler knows that as well. So whenever we have a value of that type, if we call a function and we get that as a return value, In order to do anything with a type of that nature, we have to deal with all of the three cases. We sort of have to handle all three cases. And if we don't do that, the compiler will tell us, and you can actually make the compiler, not, refuse to compile if you haven't handled all three things. So it enables us to be we can write some really robust code because we can have compile time checking of whether we've dealt with all the edge cases as well. So in general, this is known as a sum type. And functional programmers really love this because it enables them to make legal states unrepresentable. This is a catchphrase that you will hear functional programmers talk about over and over. It was coined by Yaron Minsky, who writes in OCaml, another statically typed functional programming language. But we do it in F# all the time. In the next time slot, I believe Scott Blashin will be talking about something. Maybe you'll hear him say it. He often says that with good reason. Haskell will do the same thing as well. So you may also, Scott Blashin in the next talk will never be smug, but you may, sometimes, encounter those functional programmers that can be a little overbearing and say, well, we can make illegal states representable. What about you object-oriented programmers? Can you do that? And then you say, because you've been to this talk, you say, well, yes, we can, because we can just use church encoding. All right, okay. So this is Alonzo Church. He's the inventor of the lambda calculus. And he didn't come up with this idea of church encoding himself, but he came up with a way to encode or describe mutually exclusive things as functions. And then later on, programmers sort of figured out that the way that you could do that in lambda calculus actually translates pretty well into code. And therefore, we call it church encoding after him. But he was a mathematician. He was not a programmer. So let's see how that works. So we have this thing, we sort of started on the work of doing a free monad. Now I'm going to pause that recipe. I'm going to put it aside a little while, and I'm going to pick up another recipe. And this is the recipe for turning discriminated unions into church-encoded C# code. So there's a recipe for that as well. And you can basically just, think of it as a paper, and you just follow the recipe. So how do we do that? Well, we'll take the name of the type, and we'll turn it into an interface. And here you can see that it's an I reservation instruction of T. So that, prime A up there just becomes capital letter T. So that's the generic type argument. And then you take each of the cases. Oh, I need to do something first. The next thing you do is that interface always has one method. And you could call it match. It doesn't really matter, exactly what it's called, but there are reasons why it might be a good idea to call it match. And you'll notice that this is generic as well, but it's generic on the method level, not on the type level. So there's already two different generic types involved here: T on the type and T result on the method itself. So match must return a T result value. So what you do now is for each of the cases in your discriminated union, you add an argument to this method. So what we do first is that we take is reservations in future, and we add that as an argument. And the recipe says that the argument should be a function that takes something and returns a T result value. So we do that for is reservation in future. You'll notice that I've lowercase the I there, so that it looks like an argument and not a case anymore. So we do that for the other two things. Read reservation should be a function from something to T result, and create should be a function from something to T result. So the idea here is that when you have an object of that interface, you don't know which of the three cases it actually is. And in order to do anything with it, you have to supply three functions that will handle each of the three cases. Now, only one of those three functions are ever going to be executed, but you don't know which one it is, so you have to supply all three so that you cover all the cases. So all of those functions, you'll notice, returns T results. So this is how you can sort of pull data out of a discriminated union in C# and still have compile time support. So what should go into those? You can see that sort of left a placeholder there for the input into those functions. So what needs to go there? Well, what needs to go there is the data that is contained inside of each of those cases. So we actually need more. It turns out we need more room. So I'm just ordering things around a little bit, and you'll notice that the read reservations thing actually overflows to the right, so you can't even see all of it. It's okay. It's going to be horrible, and you don't need to see all of it to see just how horrible it's going to be. So what's going to be the input things? Well, in all three cases up there, we have tuples, so we can say all of them are going to be tuples. And the first element of the first tuple is a reservation value, so we can just map that over. The second one is a datetime offset value, and the third one is a reservation value. So again, you can see I'm following a mechanical process. I don't really have to think, and I was really happy when I did this because I actually couldn't understand what was going on. So I just said, I'll just take this one and put it there, and okay, that compiles. Okay, fine. So that's there. But then the second element of the tuple, we need to figure out what to do about that as well. So you notice that they're all functions. So we'll say this needs to be a func. And then all three of them are functions that return the generic type A. It's down in our C# code we call that T. So we'll just say that's going to be the return type. And again, you can't see the middle T because it's sitting out here towards the right. But it's not really that important. So now we just need to figure out what's got to be the input to those continuation functions. Well, in the first case, it's a bool. In the second, it's an I-read-only collection of reservation. And then in the third case, it's an int. So that's the first step of doing church encoding. And if you think already that this looks horrible, I agree. I mean, this is not something when, if you just show people if you just show this to someone and says, well, you're a C# developer, can you tell me what's going on here? So, what? No. That makes no sense. It's a func of a tuple of something, and then inside of that func there's another thing, or what? So maybe we should, shield ourselves a little bit and just sort of block them out and sort of just think about them as, blobs of data. So I'll just block them out with 3 colors, and don't try to interpret anything from those colors. It doesn't mean that red one is bad and the green one is good. It's just so that we can distinguish them from each other. So we're sort of hiding the details there and just sort of try to figure out what we can do. So we have 3 functions that go from either the red data blob or the yellow data type or the green data type to T result. So the next thing we need to do when we want to do church encoding is that we have to create an implementation of this interface for each of the 3 cases. So we'll just start with the first one and say, let's create a class called isReservationInFuture. It has to implement the interface. Now, what it'll do is it'll take a tuple of reservation and func and bool, blah, blah, blah. Okay, that's the red one there. This is basically an adapter over the red data type. An adapter, that design pattern from in the Gang of 4 book, where it says, well, if you have an object of one type and you want to make it look like an object of a different type, you can create a little wrapper class that makes it look like it's the other thing. This is basically what we're doing here. We have this, whatever that red blob is, and we just make it look like it's an I-reservation instruction of T. So in order to implement the interface, we have to implement this horrible-looking match method there. And again, we'll block the things out so that we don't have to think about exactly what's going on. And then we'll have to figure out, okay, so how do we implement this? Now, we have to return a value of T result. And we have 3 functions to choose from and a value of the red data type. So we have a function that goes from the red data type to T result. We have another function that goes from the yellow data type to T result, and one that goes from the green data type to T result. Now, the only thing we can really do here is just to say, well, the function that goes from the red data type into T result is ReservationInFuture. That will work. If we call that, if we dispatch, execution back to that one by just passing in the tuple, then it's going to return a T result. And this is going to type check, so that's probably okay. When you do generic programming like this, it's basically, when it type checks, it's usually also correct. So we do that we do the same thing with the other 2. In this case, I'm just always dispatching back into isReservationInFuture. This is the function that the caller provides that will handle that particular case of those 3 cases. And we do the same thing with the other 2. Here's an adapter over the yellow data. You'll notice that it always, calls or always dispatches back to read reservations. And the third class is an adapter over the green data, and it always dispatches back into the create function, that handler there. So we can unmask this again if you think that's helpful. I don't think it's helpful, but it compiles, and it gets us towards where we want to go. But pretty it isn't. Now, what we have so far here is we have a generic type. Now, what the overbearing character there said is that we needed to create a free monad from a functor. So is this a functor? Well, a functor, the idea of a functor is just like an enumerable that you can sort of map over it. So basically the idea is that if you have an I-reservations instruction of t, can we turn it into an I-reservations instruction of t result? Well, if we have a function that turns t values into t result values, that is. Now if we can do that, then it's probably a functor. Turns out that we can. So the way that we need to do that is we have to create a select method. This is just like the select methods that are defined by for I enumerable of t. And we make it an extension method on I reservations instruction of t. And then we just, by convention, we call that function, the second argument there, we just call that the selector. All right, so how do we implement something like this? So again, functional programmers will basically tell you that when you're working with statically typed functional programming like this, you just, what they say, follow the types. You sort of just look at the generic types and if you can figure out how to connect things so that the compiler, that everything type checks, you've probably done it right. So let's see what we can do. First of all, we have source. The only thing we can do with source is we can call match because that interface only defines that single method. So we don't really have any choice, that's what we need to do. And because the C# compiler can't really figure out what it is that we're trying to do, we have to put this type annotation on and say we want to return an I reservations instruction of t result. All right, so when you're calling the match method there, you have to supply a function that will handle each of the three cases. So we can do that as a lambda expression, so that's what I'm going to do. So the first one handles the is reservation in future case. And I'm just starting the lambda expression here. So again, the t is what's inside that case. This is that tuple, that red tuple that we looked at before, that isn't particularly easy to think about, but that's what it is. So you get a tuple as input, and what you have to do is you have to produce an I reservations instruction of t result. So, so how do we do that? Well, you have three classes that implements that interface. And when we're talking about functors, we have to do what we call a structure-preserving translation. And that means that you can't jump between the cases. If you're already in this case that's called is reservation in future, you have to stay in that case. So that basically limits our options quite a bit. So we'll just create a new is reservation in future of t result. And then, if you just try to type this out in Visual Studio, that constructor will say, but if you want to have one of those, you must supply a tuple where the first one is a reservation and the second one is a function that you can't see because it's overflowing. We'll get back to that in a moment. Now the tuple, again, requires you to fill some data into the tuple, and the first data you have to put in is a reservation value. And we can do that by just saying t.item1, because t is a tuple. The first item in the tuple is a reservation value, so you just copy that over. That was easy. Now the second one is a little bit harder. What needs to go here is a func from bool to t result. So how can we produce one of those? Well, we could write a lambda expression. So I know that we're writing a lambda expression inside of a lambda expression. Yeah, that's what you sort of end up doing. So we could write a lambda expression that starts with a Boolean value. So b here would be a Boolean value. So at least this is a func from bool. So now we just need to figure out how we produce a t result from bool. So what can we do with Boolean values here? Well, we have a func from bool to t. That's called t_item2. This is a function. So if we call that function with the b, the Boolean value, we get a value of the type t. So that's not quite what we need. We need a value of type t result. Can we somehow translate a t to a t result? Oh, it's up there in the selector. So we can just call the selector, and now we get a t result from the t. So that entire lambda expression there is a func from bool to t. From bool to t result. And it looks absolutely horrible, but it gets the job done. This is actually also how you do it in F# and in Haskell. And basically, you don't have to think, this is how it's always done. There's a recipe for that, you just follow the recipe, and you do that for the two other cases, and it just looks like this. So that made everything look even worse. But again, if you're not understanding all of this, the point I'm trying to make is just that this is what your code's going to look like if you want to do functional programming in C#, that is. All right. So let's see, how much time do we have? Okay. So what we've done now, we've actually created a functor. So we know that if we have a functor, we can use a free monad to turn any functor into a free monad. So how does that work? So now I'm putting away the church encoding recipe, and I'm picking up my free monad recipe again, and we'll try to look at how does that work. So in F#, you have to then begin to type to define a type called the reservations program. So what we've defined so far is an instruction set. So we said there, our DSL has 3 small verbs or 3 small instructions, but now we would like to create small programs using that DSL. So we'll define a type called reservations program of A, and it always follows the same structure. It has 2 cases, so it's a discriminated union. And the first one is called free, and in this case, the type is of reservation instruction. That's the one you just see in the functor that we just created, of a reservation program of A. And then you say, well, but wait a minute, reservation program of A, that's what you're defining right now. Yeah, this is a recursive data definition. So get used to working with recursion if you want to do functional programming. All right, so how would you ever create a value like this? You say, well, you'd use the free data constructor, and then you say, well, I need to create one of those instructions. In order to do that, I'll need to create a program. In order to create a program, I'll need to use the free data constructor, and then you'll just keep on forever. So you need a way out. So there's another case here called pure, and that means if you want to create a program, you can also just say pure of int, for example, pure of 42, and that would give you a program of int. So you can mix those, so you can say, well, the free, and then you can create an instruction that inside of that has a pure. So you need those leaf nodes in sort of that recursive data structure in order to make it stop at some point. But this data type we can turn into a monad in a moment. But first of all, we need to figure out, okay, so how do we encode that in C#? So again, I'm going to put away my free monad recipe. I'm going to go back and pick up my church encoding recipe and say, oh, we know how to church encode this because we've already seen how to do that. So we create an iReservations program of T. We add a single match method. And now I need to add 2 arguments, one for each case. Now the first one should be a func from iReservation instruction from iReservation program to T into T result. And we call that free. And the other one should be a func from T to T result, and we call that pure. Okay, first say about church encoding. The second one is create the classes that implement the interface. In this case, we just need 2. I'll start with the simplest one, the pure one. So pure implements the interface. It's just an adapter over the generic type T. So we just have any value of the generic type T, and we make it look like an reservation program of T. How do we do that? Well, we implement the interface. There's this match method, and we always just call pure, because pure is a function that goes from T to T result. We already have a T, that's X. So if we call that with X, we get a T result back. So that type checks, so that's what we need. Now you notice we completely ignore the other argument there. So we just dispatch to that handler. Now in the other case, it's basically the same thing. We call it free of T. The data inside of it is much more complicated. But again, you can sort of just imagine that you don't really have to understand what it is. We're just having an adapter over that horrible looking thing there. And then we implement the match method again, and we do that by always calling free, because that's the only thing that will take that type of data and return a T result. So we just dispatch to the free function and always ignore the pure function. Right. So that's how we do the church encoding of the program type. So now we have a reservation program of T. Now, we're trying to figure out whether we can turn that into a free monad. So how can we turn this into a monad? What does that mean? Well, basically it means if we have a reservations program of T, we want to be able to turn it into an iReservation program of T result. You sort of heard this before. You're saying, well, isn't that just a functor? Yeah, but the translation function is going to be a little bit different. If you have a func from T to iReservations program of T result, if you can make that work, then you have yourself a monad. So in order to implement that, we'll create a method called selectMany. So you'll notice that the type of this thing and the naming of it is actually given by the C# compiler already. C# knows about these things. If you do it right, you actually get query syntax support for your node type here. So selectMany is the name. We make it an extension method on reservation program of T, and we call the function there selector, just like before. And basically what we need to do is follow the types. The first thing, the only thing we can do with the source is just called match. So you see sort of, we just go, this is very mechanical, we just go through the same things over and over again. Now, the match method takes two arguments and a function that will handle each of the cases. So we'll start by writing a lambda expression that handles the free case. And the free case, the lambda expression takes as input an I-reservations instruction of an I-reservation program of T. Now it gets a little bit hairy now. What we need to do is we need to return an I-reservations program of T result. And we need to make it structure preserving, so we need to translate the free case into another free case. So we say new free of T result. So if you do that, the Visual Studio or your IDE will tell you that what you need to put into that free of T result is an I-reservations instruction of an I-reservation program of T result. So you somehow need to translate one into the other, the blah, blah, blah of T to the blah, blah, blah of T result. Now you have this I-reservation instruction already, and it's a functor, so we know that the select method can actually be used to translate the thing inside to another thing. So we call select on that. That's the extension method that we just created before. So inside of that is a program, an I-reservations program of T. So how do you get an I-reservations program of T result out of that? Well, you will notice that the method that we are writing at the moment takes as input an I-reservations program of T, and it outputs an I-reservations program of T result, which is exactly what we need. So we're just going to call the selector, we're just going to call select many with the selector, and that's it. So you go, doesn't it call itself? Yeah, it calls itself. It calls itself recursively. So, but how is that ever going to end? Well, it's going to end because sooner or later it's going to run into that pure thing there, and then it's just going to say pure is a T value, and we just turn that into an I-reservations program of T result by calling the selector. And that, at that point, the stack can unwind, and it can go back to all those recursive calls to select many. So you say, well, but still, doesn't it mean that all of that recursion, couldn't you blow the stack? Yep, you could blow the stack. But that's not nice. I know, it's not nice. This is why you don't want to do functional programming in C#, because eventually you will have to deal with recursion, which is a normal thing in functional programming languages. And languages like Haskell and F#, they have a language feature called tail recursion, so that if you write your recursive algorithms in the appropriate way, they never blow the stack. But C# doesn't have that feature, so even if you do all the things right, you could still blow the stack. So that's another reason why you don't want to do functional programming in C#. But still, okay, in this case, when you're doing free monads, the stack tends not to get that deep anyway, and not in this example anyway. So we can just push on and see if we can get things done. But select many is now implemented, and then this means this is a monad. This is basically what a monad means. We don't have to make it particularly magic. This is basically what we need to do. Right, so the last few things that I need to do in order to be able to complete all of this stuff is I'm just going to add a few helper methods. So before, when we used dependency injection, we had normal methods that we could call, like is reservation in the future. You pass a reservation to that, and that would have returned a Boolean value. Now, what we want to do instead is we want to be able to create small program snippets of this little DSL that we are creating at the moment. So we're creating a little helper function here that says, when I call is reservation in the future with a reservation, I get one of those program snippets, and then I can compose those with other program snippets because it's a monad and monads compose. So if we were to do this in F#, it would be a one-liner. This is basically what that function looks like in F#. Translating this function to C# looks like this. This is the same, but because C# is not really designed to do all of the fancy type inferences that the F# compiler can do, you have to do all of that type annotation with all the generics. So that one-liner turns into all of that thing. And the same thing goes for the other ones. If you want to create static helper methods for the other two cases, read reservations tend to look like this. I'm not even going to walk you through this. And create looks like this. So, this, as you may have noticed so far, creates quite a lot of boilerplate code. But we can now rewrite try except as a pure function. So the idea here is now that it takes a reservation as input, that's a pure value, but instead of just returning a nullable int, it returns a program of nullable int. And that means, that's actually a little abstract syntax tree that describes what you want to happen in various different cases. And then you can run an interpreter over that little abstract syntax tree. And then whenever you encounter one of those instructions, you can go and query the database or query the system clock or whatever. And that's sort of how it works. So this is a fairly normal thing to do in Haskell. This allows you to sort of push all your impure I/O to the boundary of the system. Now, the way that it ends up looking in C# then is you say, well, let's start by figuring out whether the reservation is in the future. So we call isReservation in the future that new static helper method that I just defined, and that is not enough. We need to do more because this just returns an iReservations program of bool. But what you can do now is you can, just like in the TPL example that I showed you before, you can now say, well, when this is done, when that evaluation is done and the Boolean value has been produced, I can now provide a continuation. So in the TPL example, that continuation was called continue with. But now, since this is a monad, we can call select many instead. And the input to the continuation is the output from the previous step. That's just a Boolean value. And that means we can now switch on that, or we can do an if evaluation on that and say if that's false, we'll return a new pure of nullable int because pure implements iReservation program of T. So this is an iReservation program of nullable int, pure is, that is. Now, otherwise, we can continue and say, well, if we are not exited at this point, we can return, continue with the next thing. We can call read reservations, another one of those small static helper methods that I wrote. And this will then create a program of collection of reservations. And then you can do a continuation of that as well, and that's going to be RS. I'm not even going to try to attempt to talk you through this. It looks horrible, and that's the point. All right. We're basically done, but I want to say a few more things before we wrap up. Now, you may say that this is an iReservation instruction. This is a church-encoded discriminated union. You could say that I'm building up a little bit of a strawman argument here because I've made it unnecessarily functional and it's not properly object-oriented. I can actually refactor this into something that's more object-oriented. So it turns out that this is really just a disguise of a very well-known design pattern. You may have noticed that I said dispatched quite a few times. All that's going on here is double dispatching, so you can refactor this to the visitor design pattern. So what you end up having then is you have iReservation instruction of T that just has a single method called accept. It's no longer called matched, it's called accept. And then you have that auxiliary interface definition that defines the visitor, and it has three methods that are handlers for all of those three cases. There's still some inline functions there, but we've actually made it more object-oriented, if you will. And we can do the same thing with the program. We can refactor that into a visitor. And we can also do it the other way. So this is what we call an isomorphism. You can always take a church-encoded discriminated union, turn that into a visitor. You can always take a visitor and turn it into a church-encoded discriminated union. It sort of goes both ways. There's no loss of information going back and forth there. So this is basically why I called the talk here Dependency Injection Revisited. The point is that you can refactor your dependency injection-based code to just return something that is a visitor where the visitor walks over a little abstract syntax tree. Why you would want to do that, I don't know. I mean, that would be absolutely crazy stuff, I think. I just did it because I can. The try accept method here doesn't change whether you use the church encoding or whether you use the visitor variation. It doesn't change, so that just remains the same. So you may say now, well, but this seems really difficult. Is functional programming, is it really like that? Is it that hard? And no, it's not. In Haskell, it would look like this. But this would be it. There would be no boilerplate in Haskell. This would just be the function that I write. All the things that I pull in, all the data types and so on, there's a few of my own, like a reservation, for example, is still, my own domain type. But apart from that, turning that into a free monad is just one line of declaration saying, here I have something, I'll turn it into a free monad, bang, it's done, and I can write code against that. There's no boilerplate there. And you can do the same thing in F#. That requires a little bit more boilerplate because there are things you can't automatically do in F# that you can do in Haskell. But it still looks fairly pretty, I think. Now, I did say that in C#, by writing select many in the appropriate way, you could use query syntax. This is basically what we're doing here. We're sort of letting the monad, fade into the background because we have some, syntactic sugar in Haskell and in F#. So we can say, well, but we do have syntactic sugar in C# as well. We can use it. We can use query syntax. So we could rewrite the try except function to look something like this. So this uses, query syntax. You'll notice that all of these return blah 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 from return from blah 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 in blah 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 from blah 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 in blah 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 and so on. So this works, but it's not pretty. And I had to stack monads in order to make it work because one limitation of the C# query syntax support is that it doesn't allow arbitrary branching inside of the the query syntax. So in order to deal with branching, I had to turn the nullable int into a maybe, which is a monad in its own right, and then I had to define a stack of those two monads, which resulted in even more boilerplate code. So it just grows and grows and grows and grows. And then even so, it's not really pretty because you have to resort to using those underscores and double underscores and so on in order to get the code to compile. So I would say that this works. It executes. It compiles. It is the way you can do it. But if you hire a new developer and your manager says, well, I've hired this new developer. She or he has 10 years experience with C#, so she or he is going to fit right in. And you say, well, okay, here's the code. This is our code base. Go figure. It's not the syntax. The syntax doesn't really help you here, knowing the C# syntax because the abstractions are completely alien to what compared to what most people are used to. So how do I do functional programming in C#? Well, you don't because C# is an object-oriented language. Fine, it's object-oriented, but it has lambdas. How do I write strictly functional code? Well, you use church encoding to make illegal states unrepresentable. Well, did you just tell me to go fuck myself? I believe I did, Bob. So the point that I'm trying to make here is not, C# has many good features, and some of them were inspired by functional programming, like lambda and like link and things like that. And I'm not saying you shouldn't use those features. The C# language design team very carefully picks those features that they think fits into the C# language, and they port those things over. And there are other things they're sort of leaving over on the F# side or the Haskell side because it doesn't really fit the language. So using the things that are there, in C# I think is perfectly fine. So I'm not trying to say that you shouldn't adopt some sort of hybrid approach. But if you really want to do functional programming, you have to realize that C# is not the environment for that because it's not designed to do that. If you really want to do functional programming, you should really use a proper language for that. And I understand that it can be difficult because you're in an organization and you have managers and so on. But still, I think it makes no sense to try to do it in C#. It would make sense to do it in other languages. I really love functional programming, but it needs to be in the right language. So I'll stop talking. If you have questions, I'll be happy to answer the questions. I think you can just come and talk to me if you have. And those of you who want to get lunch a little bit earlier than anyone else, you should just rush out of the door now. But please remember to fill in or put the evaluation things in when you leave. So thank you for coming, and have a great conference today and tomorrow.
Very beginning, why did you turn the interface into a DU, not just use an interface?
Well, you absolutely can do